Hello, everybody. Today we begin a series of lectures on search methods in artificial intelligence. Artificial intelligence is concerned with automated problem solving. When we talk about automated problem solving, we mean that instead of defining different algorithms for different problems, we are looking for a unified methodology which can be used to solve a large class of problems. So, in these cases, the problem description itself is the input to the problem, and the search algorithm or the automated problem solving methodology tries to find the solution to different problems using a systematic approach. This method of automated problem solving has got various facets in artificial intelligence, and today we will discuss one of the core facets, which is the use of search methods, and this we will do in a series of 3 or 4 lectures. Today is the introductory lecture where we talk about the automated problem solving method and the search spaces created. Let us discuss a few very complex problems and their solutions which we find in everyday life. Let us consider the pathfinding problem. The pathfinding problem, all of us who use mobile phones use some technology to find a route from one place to another. This, as you know, is a very complex problem where millions of people are trying to find routes from one place to another. So the input to this problem is a map. This map consists of locations. This map consists of streets or roads. And given a start position and a goal position, there is a need to find an accurate, shortest or most convenient path. So this is a problem which people try to solve by running some shortest path algorithms over large graphs. And when we look at city maps, country maps, road maps, you can imagine the number of locations, the number of streets, and this complexity and the size of this problem. So typically this problem could be solved by a single algorithm, but it could also be looked upon as a generalized problem that we want to solve by automated problem solving. Let us consider the second complex problem. Chess, as we all know, is one of the most complex games which require a high level of intellect and practice. Now for chess, there are various specific programs which are chess playing programs, and we know that there are chess playing programs which beat human world champions. Now, what is the structure of the chess playing program? There is a board, there is a set of pieces who are in their locations, there are a set of moves that can be played, and there are a set of 2 players who play their turns one by one. And we all know what is the starting position is known to all. However, the goal position varies depending on whether there is a win or a loss for somebody or a draw. So again, here is another very, very complex problem for which individual programs can be written for solving this problem, and for which there are various techniques to write good programs. Let us look at the third problem that we have, which we call robo assembly. Now here a set of robos, as you can see in the picture, are trying to manufacture a car. These robos are pre-programmed robos who have a sequence of actions that they need to take to manufacture this vehicle in terms of welding, fitting, turning, shaping, painting, etc., etc. Now, if we look at a program which is trying to write this, we will notice that such a program can be written, but the features of this program where every robo will have its own actions. Each robo will see the whole scene analysis and then perform a coordinated series of actions. This coordinated series of actions finally reaches the goal. The starting position could be defined as the base frame of the vehicle, or a vehicle with its components partly done, and the finishing could be defined, and the goal state could be defined as the completion of all the actions to do this vehicle. In addition, in all these problems, every state, every action is constrained. In the pathfinding problem, you can only move along streets, and then there are more details about street congestions, whether a road is blocked, etc., etc. In the chess playing program, you have valid and invalid moves, moves that are only valid moves can be done. And in a robo assembly, you have a full series of coordinated actions. So we will slowly see that even though these problems have individual solutions, there is a commonality among these problems which enables us to find a common approach to solve all these problems. Let us see a few more problems. We all of us use a circuit board or a chip, and in a chip there are millions and trillions of transistors connected to each other. This diagram which we see here is just a diagram of a layout of a chip. Now a chip consists of components, and then each of these components need to be connected by wires. And when there are billions of components and they all need to be connected, then we notice that it is a very complex problem of being able to place the components. So there is a placement problem. Then there is a routing problem. So the first is, where will we place the component? The second is, after we place the component, how will we form the paths and the routes of the wires, so that given a 2-layer, 3-layer, 1-layer board, the wires cannot intersect on the same plane. And then there are more complex scenarios of multiple points being connected by the same bus or the same connection, and so on and so forth. So here is another problem where, given a set of components which is the start state, you have to solve the placement problem and the routing problem. And there are millions of constraints that we have to satisfy in order to meet this, along with some optimization constraints. And these optimization constraints are optimization of wire length, optimization of area, optimization of power, ensuring that sufficient speed of the circuit is there, and so on and so forth. We come to the fifth problem of our example category. All of us have nightmares doing timetable scheduling for a large institution. As you can see, there will be about 10,000 students giving exams simultaneously or taking classes simultaneously. And for each of these courses, there will be about 500, 600 courses running. Each course will have a slot in the week of every week. And then there will be some rooms. Every class cannot be allocated to every room. And therefore, the students need to be dispersed so that nobody has only classes in 2 days. So we have to have a problem where we need to schedule or allocate classes to rooms, time slots, teachers, and students in such a way that there is no clash and certain constraints are satisfied. Here again, the timetable, a blank sheet forms the start state, and all slots correctly filled up form the final state. And then there is certain constraints which have to be satisfied, certain optimization rules that have to be done. And therefore, here is another very complex problem which needs to be solved. Let us come to our last example problem in this category. Our last example problem in this category is symbolic integration. We all know that there are programs for numeric integration. But suppose I want to solve it like we solve in our own way when we solve a problem given a symbolic integration problem like x squared plus 3x plus 5 integration dx. What is the solution to this? So we want a symbolic solution to this. Now in order to do a symbolic solution to this like a human being, we have to know the rules. So there are various rules of integration, and all these rules can be applied at various stages. Not every rule can be applied at every stage. And based on the applicability of the rules, we may try to do it in a number of ways. The objective is to find a proper sequence of the rules from a given start state, apply the rules, and reach a final state, which is the final integration solution where the integration sign is removed. So here we have 6 problems where we can have 6 types of solutions, but we would, as we have observed in each of these problems, there is a commonality in them. Each of them talks about a configuration. Each of them talks about a set of rules or moves that can be made to change the configuration. They talk about constraints which must be satisfied either in a configuration or while changing from one configuration to another configuration. It talks about some optimization that needs to be done. And then, given a start state and a goal state, we need to apply these moves or rules which change one state and transform from one state to another state and move on to form the final solution. So we now come to the automated problem solving by search. This is the topic which we are interested in. As I have just mentioned, it is a generalized technique for solving large problems. Here, instead of every problem having its own solution, the problem statement is the input and the solution is the output. Sometimes even the algorithm which finds the solution could be the output. As we have just seen, that this problem can be formulated by these things. One is the concept of a configuration or a state. That means we would like to define a configuration or a state. Then we need to know what are valid states or configurations. For example, in the timetable situation, certain configurations are not valid. For example, we cannot have the same room allocated at the same time to 2 classes. So certain configurations are valid and constraints have to be satisfied. Then there are rules or state changes that need to be taken into account for converting from one state to another. For example, in the chess playing program, every state change consists of a valid move of one entity, whether it's a queen or whether it's a pawn or whatever it is. On the other hand, in the timetable scheduling problem, you will see that every allocation, tentative allocation of a slot to a class, to a teacher, to a student is a move. And so on and so forth for all the 6 examples that we have seen. Then we have an initial configuration, which is the start. And then we have a set of goal satisfying configurations. That means given a configuration, we can check whether that is a goal or a solution. So based on this set of configurations and rule changes, we create what is called an implicit state space. The state space consists of all the states in the system, and there is a connection from one state to another state by a valid state transformation rule. This implicit state space is implied by all these items. That means the rules of state change, the validity rules, and the initial and the goal state. And given a problem description in such a manner, we are requested to find a valid solution from start to goal in this implicit search space. Obviously, this implicit search space is extremely large. Therefore, opening up that whole space and putting that whole space in memory and then trying to find that solution is not a correct approach. Search methods try to open and unfold this implicit search space, intelligently search it to find a path from start to goal without looking at all possible states. And the issues, as I said, the size of the implicit search space. The other thing is that every problem has its own domain specific knowledge. For example, there is knowledge about chess, there is knowledge about path planning, there is knowledge about wire routing, there is knowledge about integration, there is knowledge about timetable scheduling, and so on and so forth. How can we capture domain specific knowledge in our system? And finally, we need to find intelligent algorithms that work in reasonable time and memory. And then we have many other issues of incompleteness and uncertainty that we face in real life. So our approach is automated problem solving by search, by which a problem statement is the input, and given the description of the problem in terms of state transformation rules, valid configurations, and other aspects, we then try to find a path from start to goal. So we try to find a unified method to solve a complex set of problems. All of us know this famous problem. It is called the Tower of Hanoi's problem, and I have extended it. It is also known as the Tower of Brahma, and I would request you to have a look at the story or the legend why it is called the Tower of Brahma. Typically, this problem has got n disks, and 1, 2, 3 pegs. I have added a 4th peg here. Now these disks are given in this order, and you are to move the disks on these pegs to take all the disks from this peg A to all the disks into this peg D. So the rules are never should a larger disk be placed above a smaller disk. That means we cannot put this topmost disk here and the next disk above it. So this is the rule. Many of us know what it is. So in this problem, we know what is the configuration. The configuration of this problem, or configuration or state tells us that if there are disks numbered 1 to n and there are pegs numbered A to D, then the configuration will tell us which disk is on top of which disk on which peg. And obviously you have the configuration constraints. As we mentioned, one constraint is this, and then there are other constraints. The same disk cannot be in multiple pegs, and so on and so forth. And what are the rules? The rules, the state transformation rules, are moving the topmost disk from one peg to another. That means you can move a topmost disk from this peg to another peg, and if that was partially full, it will just go onto the top of that. And given an initial configuration and a goal configuration, you can see that all the possible configurations that we can form by making a set of moves from the state space, which is implied by these rules, and the input to our automated problem solver is the set of rules and the configuration space, the valid configurations, and the general algorithm tries to find a path from the start configuration to a valid goal configuration using a valid set of moves. And we also want to find the shortest number of moves. All of us know that if there are 3 pegs, there is a unique correct solution. On the other hand, if there are 4 or 5 or 6 pegs, there can be many solutions to the problem. And in these many solutions, we would like to find the smallest solution. In order to understand the state spaces better, we are taking up a smaller, a more toy problem. This toy problem says that there is a bucket full of water and there is an infinite supply of water in this bucket. There are 2 jugs, J1 of volume 3 liters and J2 of volume 5 liters. So J2 is a bigger jug and J1 is a smaller jug. And all the things that we can do are, we can fill a jug, we can empty a jug, we can fill a jug by putting that jug in the water tank and filling it up. We have no markers on the jug to indicate how much we want to fill up. Either it will be fully filled up or it will not be filled up. Empty similarly pours the water back from the jug into the tank. And you cannot partially pour the water, you have to either pour it fully or not. Then there is a third thing which says that you can pour water from one jug to another. And there are 2 conditions by which you can pour water. One is the jug that you are pouring from either becomes empty, or the jug that you are pouring to either becomes full. So these are the rules of the game, and therefore we define the configuration or state by what are the values of water in each of these jugs. And then we have our state transformation rules. For example, if I want to fill J1, then from J1, J2, it will become 3, 2 because J1 can be filled by 3. If I fill J2, then whatever is J1, J2, it will become J1, 5. Similarly, empty J1 will be, if the configuration is J1, J2, it will become 0, J2. Now, pour J1, J2. Pour J1, J2 is, if J1 is X and J2 is Y, then if J1 is X and J2 is Y, then either J1 will become 0 or the total amount of the total amount of J1 will go into Y. So which means either this becomes 0 and this becomes X plus Y, or this becomes 5 and this becomes whatever is J1 X plus Y minus 5. So this is what happens. So you can fill up. So you can now define the state transformation rules. You can define your start state, which is 0, 0. And you can finally say my goal state is when the first jug has 1 liter and the second jug has nothing. So let us now see how these state transformation rules form the state space. These state transformation rules imply the state space as follows. Each of these states, only the partial version of this state space is drawn here. The full state space is not drawn, but this will give an idea of what we want to say. So 0, 0 is the starting point when nothing is there. If we fill up jug J1 from 0, 0, we go to 3, 0. Or if we fill up J2, we go from here to here. And then we can again empty. Let us go to a bigger picture and understand this a little better. So let us try to get a better idea of this. So if we are at 0, 0, then here if we go this direction, then we are filling J1. And if we go in this direction, we are emptying J1. Similarly, this fills up J2, this empties J2. That is why these arrows are all bidirectional. Now this one from 3, 0 to 3, 5 is also a filling up of jug 2 when jug 1 is already 3. On the other hand, from 3, 0 to 0, 3 is a pouring of water from jug 1 to jug 2. On the other hand, from 3, 0 to 3, 3 is when jug 2 has 3 liters and jug 1 is filled up from the tank. And we can go on and so forth, and we can try to find a sequence of steps. For example, from 0, 5, this one is a pour from J2 to J1, which means J2 cannot be filled up by more than 3. So this fills up it by 3 and this remains 2. Then from here you can pour out all the water. Then you can transfer these 2 liters to jug 2. Then you can again fill up jug 2. This you transfer from jug 2 to jug 1. Then from here you can again fill up jug 1 and so on and so forth. And then we need to find a sequence of these moves to reach my goal state. So this state space, which is a small state space in this toy problem, is actually an enormously large state space in all the 6 problems that we have discussed. The goal is that given the implicitly defined state space by the state transformation rules, how do we find a path from start to goal without going and generating every state in the state space? So let us look at some very complex problem. This is the Rubik's Cube problem. And every move which you turn in the Rubik's Cube forms a state transformation rule and the state space. And looking at the number of Rubik's Cube configurations, you can try and find out the size of this state space. And you will notice that this is a huge state space of various moves that can be done, because at a particular state there are several moves that you can make around in terms of turning some vertical or horizontal or in some direction. There is the famous n queens problem. That means you are given a grid and in this grid, in the queens of the chessboard can move in the horizontal, can move in the vertical and can move in the diagonal positions. Therefore, we are to place a set of queens which do not attack each other. Suppose I place a queen here. Obviously, I cannot place a queen in any of these places or any of these places. Nor I can place a queen in any of these places. But I can place a queen here because these 2 queens do not attack each other. Now if I place a queen in this place, then I cannot place in these, I cannot place in these, and I cannot place in this, and I cannot place in this. So the only place I can put a queen is here. Now if I put a queen here, then here the 4th place that I can put a queen is here, and the 5th place that I can put a queen is here. So given an n by n grid, how do I place queens? This forms a state space by the grid being empty at one point in time, and placing the queens in different positions will give you different configurations and create the state space. All of us are very aware of this third problem that I'm talking about, is the famous noughts and crosses problem. I can put noughts, and this is a two-player problem where two persons, one puts a knot and one puts a cross, and we know these famous configurations that if somebody puts it here and somebody puts it here, then again this is how the game goes. So based on the configuration of the game is this 9 slots, and which place has filled up which slot. We know what is a win for a player who puts X, what is a loss for a player who puts X, and we know win for one is loss for the other, and we also know what is a draw position. This is a famous game that we all play, and this, as you can see, creates a state space which is of this nature. So from this configuration you can go here or here or here, here or here or here, and then from this configuration you can go here or here, and so on and so on. So we see state spaces. Let us see the Tower of Hanoi problem again with 3 discs and 3 pegs. So initially there are 3 discs, green, white and red, all on peg 1, peg A. Then I can move this red to peg C. So from this configuration I move to this configuration. Then from this configuration I can move the white one to peg B, and I move to this configuration. So this is my 1, this is my second configuration, this is my third. From this third configuration I can take the red and move it over to the white, and I get my 4th configuration. Now I take the green and move it over to the third peg, and I get my 5th configuration. Then from here again I take the red and move it over to the first peg, and I get my 6th configuration. Then from the 6th configuration I take the white on the green, I get my 7th configuration, and then finally I get my 8th configuration. So from 1 to 8 in 7 moves I can go. But this is just one sequence. I could have applied many other sequences, and this diagram, as you can see, gives me a description of the whole state space of the 3-peg, 3-tower Hanoi problem. But when we have large number of pegs, discs and large number of pegs, then this state space explodes in size. The rules, however, are small. They tell you under which configuration what move is possible. The rule is generalized. It does not work on every state. It is a set of rules which can be defined in a compact manner. Let us look at a manipulator arm. We had earlier seen the robotic arm problem. And then if we drill down in more details into the robotic arm problem, we will see that the robotic arm has got these 5 joints, as we can see here, these 5 joints. And in each of these 5 joints, there are certain moves possible. So there are moves on these joints. And therefore, given a particular configuration, for every move, I will transfer from one state to another state depending on the moves. And by these sequences of moves, I am supposed to do pick up, put down, turn, and when there are multiple manipulators, I need to ensure that given a space, nobody hits each other. This problem then gets magnified into a larger problem where people try to solve a more complex planning problem. And in this complex planning problem, we try to work out when we will go to the market, when we will do something, and so on and so forth. So again, the planning problems in AI again use deduction along with state spaces to solve a very complex search problem, and we shall come to this when we discuss planning in AI. Currently, we saw all state spaces were paths, but every move need not just be an OR move. That means this is not necessarily an OR move. All the previous examples that we have seen make a move either this way or this way. But there are certain things where we need to compose a solution from its parts. And in such cases, the state transformation rules will be AND, which means that if I have to reach this state, I have to compose these two. If this is A, this is B, and this is C, then I have to compose A and B to form C. That means it is no longer a path, but a combination of a path. For example, if Q or R implies P, then I can take either this route or this route. But if I say Q and R implies P, then to solve P, I need to solve both Q and R. So now, instead of having only a state space which has got OR paths, like before, we could have some spaces which have some nodes which are AND nodes. Therefore, if this is my goal and this is my goal, then one solution to this problem could be this, because I have reached the goal by, but this cannot be a solution because this node is an AND node. And to solve this node, I need to solve both its successors. So I have to solve this successor. This is an AND node, so I have to solve this successor. This is an AND node, I have to solve this successor. This reaches this goal. From here, I can take this path. So this green solution now is my actual solution because now I have got AND nodes. In an AND node, I have to take all the children of the AND node in the solution. So the state space could be an AND or state space. We will come to AND or state spaces later, but as I just said, that normal state spaces, most of the problems are OR state spaces, but there are several problems that we face which lead to AND or state spaces or compositional problem solving. Another important area which is of concern and importance is at a particular state, you need to satisfy the constraints of that state. And we have seen in various timetable problem, in the timetable problem we noticed that in a particular state we cannot have a clash where two teachers or the same teacher has got a class at the same time slot, or the same room is booked for two classes in the same time slot. So in order to do that, we have to solve what is called the constraint satisfaction problem. In general, the constraint satisfaction problem is also a very important problem in automated problem solving. I will take you through 2 or 3 cases. Look at this crypt arithmetic problem. Here I have written a crypt arithmetic solution to a multiplication problem where every alphabet in this solution is a unique digit from 0 to 9. So I have to now map O, B, M, E, Y, I, L, etc. R to a unique digit. No two alphabet letters can have the same digit, and I have to solve this multiplication problem. So this is a crypt arithmetic problem where I need to do a consistent labeling. The other problem all of us have seen in scene analysis today with face recognition, object recognition, we are supposed to recognize objects, And obviously, while we are trying to recognize objects and label objects, we would like to ensure that there is consistency. For example, if this is a car and this is a wheel of a car, we are supposed to be able to label this as a wheel and not as a dog, unless obviously the dog goes under the car by an accident. So this is a scene analysis problem, can also requires consistent labeling and satisfaction of constraints. One of the most popular consistent labeling constraint satisfaction problem is the crossword problem. In this example that I have shown for this crossword problem, here I have got numbers 1, 2, 3, 4, 5, 6, 7 and 8. And I have to fill them up. 1 means from 1 I have to fill them up with a word. From 2 down I have to fill them up with a word. And the list of words are given here. So how do I fill up a word? For example, if I filled up 1, I cannot fill up 1 with anything but a 5-letter word. And let us say I filled up 1 with laser, suppose. If I fill up 1 with laser, then 2 down is also a 5-letter word, which I have to fill up with something that starts with S. Let us say I fill it up with sales. Then constraints get generated where 4 across needs to have I in its middle letter and needs to be a 4-letter word. So that is possible if I choose line, L-I-N-E. Also it means that 7 across is a 3-letter word and has to start with L, which I could choose Lee. Now, in order to solve 3 down, it must start with R and must match here and here. And if you notice that there is no 5-letter word R, which means that this configuration cannot be solved. So our objective is here is to assign every number to a word which satisfies the size and the constraints that are along with it. And when we discuss constraint satisfaction problems by search, we will see how these problems are solved efficiently. So let us come to a summary of what we have been trying to say. Our states, we have the following things in automated problem solving. States, we have a set of state transformation rules. Now these state spaces are formed, there are solutions. The states could be full or perfect information. That means everything about the state space is known to the party. In this one, or in the game of chess, the whole state space is very clear to everybody. You know what this state space is, it's a perfect information. But there is a difference between this state space and this state space. This state space is a single player state space. There is only one player who makes a sequence of moves, whereas this state space is a 2-player state space. So it could be single player or it could be multiplayer. There are other games where there are more than one players. Let us come to this control plant. This control plant has got a set of variables. All the variables in this control plant are not observable. Nor are they controllable. So they are neither observable nor controllable. You can see some temperature, but maybe for the boiler exactly how much heat is there within the boiler, you won't have a meter to test it. You will have some meters to test at certain points, but for your whole state space configuration, this is a partial information game. So this is partial information. Secondly, this, whereas in the previous two, which we have seen, if you make a move, then that move is deterministic. In both these, if you make a move, exactly that move happens. But here, because all variables are not controllable, if you change one variable, you really do not know the exact next state of everybody else because you don't know the values of the other variables. So your situation is non-deterministic. Let me give you another simpler example of a state space. Suppose you press the brake in a car. Then the car may stop, maybe by 95% chance or 99% chance the car will stop. But there is that 1% chance that there will be a brake fail. And because of that brake fail scenario, we will not have a deterministic output. We can either have a non-deterministic output or a probabilistic output. Then there are games which are multi-party games. Imperfect or incomplete information. Look at the game of cards where 4 players are there playing a game of bridge. Here we have 2 players forming a team on one side, 2 players forming a team on the other side. And even you do not know your own team players' cards, but you can guess them by a round of bidding and things like that. So your situation is that you are playing as a team, you do not know the complete state space, and you need to make a move. And when you make a particular move, you really don't know what move your opponent is going to make or even what move your partner makes. So state spaces can be very complex. State spaces can be full information, partial information, incomplete information. The outcome may be deterministic, non-deterministic, or probabilistic. There can be a single player, there can be multiple players. Your multiple players could be your collaborators or your adversaries. And the solutions that we find in the simplest case, as we have seen, are paths, but in general we have seen in AND/OR graphs could be subgraphs. And in probabilistic scenarios, you cannot really define what will be the exact length of the path. Therefore, you'll have to go to expected outcomes. Then there are optimization criteria, the sizes of the state space, and the domain knowledge. So under this scenario, we would like to find generalized methods by which the problem description, the domain knowledge, the state transformation rules are all given as input. And for every problem, we would like to use a common generalized methodology to find the solution to that problem. That is the foundation of search in automated problem solving. We will then discuss all this in more details. Here is another problem, which is the plate cutting problem. The plate cutting problem has a set of plates which we need to combine into a sheet. And since this is a compositional problem, if I take 2 such objects into one sheet, this is one part. If I take another object and I place it like this in this sheet, this is another part. And I could combine them in OR, and then I could take another combination of, this is object 1, 2, this is object 1, 2. And these combine, either I do it this way or this way. And suppose this is object 3 and object 4, then 1, 2 and 3, 4 can combine in AND. So similarly, you will get a compositional AND/OR graph out of this problem. So as I said, it could be an OR graph, AND graph, adversarial, probabilistic. So there is a rich set of search spaces that we need to explore by our automated problem solving methodology, and we shall systematically see this in search. Thank you very much.